Alright, this video is going to take a look at the Module 9 Lesson 3 example problem. Alright, so if you are looking at this problem, initially it might look somewhat confusing or concerning, but probably the first thing for us to do is simply to identify the place where the system would rotate if it could, and our assumption would be that would happen here where it's attached to the wall. And then what we would look at is we would consider the fact that in order for this to be in static equilibrium, both the forces and the torques would need to be balanced. In order to show that, let's take a look at the different forces involved here. And okay, so you would have the component Rx here and Ry here, and also Ty and Tx, and the force of gravity pulling down on this object, which is recognized here. And then you also have this other object that is being hung from this particular location. It's not quite at the end of the horizontal bar that's going out, but it is there, and so we would also need to account for that. So if you're summing the forces in the y direction, then you would have Ry and Ty, both of those point upward, while you have the mass of the bar downward times gravity, as well as the hanging mass times gravity. So that's where this portion of everything comes from. Right, it appears and so they sum the forces. This is for the y direction, and then this one is for the x direction. And recall that the angle given here, so theta, so Ty would be T sine of theta, and Tx would be T cosine of theta, which would certainly give you a way to find the value of Rx, that is. Alright, so next we would sum the torques. I'm going to use a different color here to circle the forces that could actually apply torque. So the lever arm in this system would extend out along this this moment arm, or bar, whatever I've been calling it, a bar up until this point. So the forces that could apply torque would be the ones that are perpendicular to that moment arm. Now, Ry could not apply torque because it's applied at a distance of 0. If I was thinking about this, I would think about it as being kind of like the force that's holding the end of the bar up and keeping it from sliding down the wall. So our forces that we need to account for with torque are there, circled in purple now. And torque is force times distance if you have a completely perpendicular force, and that would be where these quantities in the torque summation come from. Now, if you move down a little bit further, they say that they've solved for the variables of interest here. So this equation was solved to get Rx equals Tx, and then this equation was solved to get Ry, and then this equation was solved to get Ty. So that's where all of those came from. Alright, this equation appearing might seem a little bit perplexing to start with, but if you remember from the other side that Ty equals T sine of theta, then you could pretty easily solve this for T, and you'd see T equals Ty over sine of theta. So what they did is they took equation 3 here, and they plugged equation 3 in place of Ty, and then this next equation also may initially appear to be perplexing, but it's not. So if you recall that you had Tx and Ty from the other page, then T, and which I don't even need to include the T, so let me get rid of that. Just for the sake of understanding that there is a triangle here, and this is the angle theta, I will always draw the dashed line there. So this, the relationship between Ty and Tx, you could do tangent of theta equals Ty over Tx. And then this expression would make sense because they've just solved it for Tx, and then again they took this expression for Ty and plugged it in place of Ty. So now I have an expression for T and an expression for Tx, and both of these are fairly complex. Alright, I'm going to switch over to green just because I have a lot of red already. So the Rx equals Tx, so that's pretty straightforward, as they just took this expression and substituted it in place of Tx. So now I have something that Rx is equal to, and they simplified a little bit by factoring out the G and then moving the tan, the tangent of theta up, but nothing extraordinary has happened there. Down here they took the Ry expression from up here, and attempt to draw an arrow and bring that down here, or to show that it comes down here. And once they did that, they took the expression for Ty and substituted that in place of the Ty right here. So and then they I guess combined such that everything's factored by G now. And then down here we have, okay, so to back up a moment, so we have Rx and we have Ry now. And in order to get the magnitude of force R, then you could just do Pythagorean theorem. And fairly complicated form here that it takes on, but it's just Pythagorean theorem with these really fancy forms of Rx and Ry that we've solved for already. In looking back at the problem, I think that the the solution doesn't really match or really goes beyond what you were asked to solve for here. Because it simply says find the tension of the cable and the forces on the wall. Well, I guess we did both. So let's go back and see if we can find those things. The tension of the cable, well, there it is. And providing you know the masses and G and the angle, you could figure that out. And then the forces at the wall, so you have Rx and Ry and also R. So hopefully that clears things up. There's a lot of algebra in here. I wouldn't expect to see anything this involved algebraically on the exam, but the individual steps here aren't they're not impossible to follow along with. It's just kind of tedious and maybe not particularly intuitive.